All right, so optimization is another application of derivatives, and basically you're trying to find the best solution. It's a process of finding a max or min value as a solution to a problem. Okay, so thinking about the general process. The first thing you always want to do is put down your knowns. Okay, and specifically you definitely want to make sure you include an equation. So I'm going to say and find an equation for the value you are trying to optimize. Okay, second step is you know that this equation that you have should have either a relative max or relative min based on the graph. And you know that your first derivative would equal 0 at that max or min. So what I'd recommend is probably at least look at the graph. Of the equation, and then I'd say use the first derivative by setting it to equal to 0 to find max or min, depending on what you're going for, value of your equation. And then the third thing is obviously you're going to use your max and min. X values, or yeah, use the max or min X values to find your solution. Okay, make sure to actually it makes sense. Kind of think about what the solution is, and then go from there. So if you want to look at a couple of examples. Number one, I'm going to ask you to find the length and width of a rectangle that has the given perimeter, and it's going to be 100 meters, and a maximum area. Okay, so if you think about the situation, kind of the first step here is you have some sort of perimeter, and I don't know how you want to label length and width, but I'll just label them I'll label them as L and W. Okay, now it says that it has a given perimeter of 100 meters, so I put down that I know that 2L plus 2W equals 100, and I know that I also want to maximize my area. Area equals length times width. Now, usually it's best to have just one equation in terms of a variable, so what I'm going to do is I'm going to solve for, doesn't really matter, solve for L, I guess. So if I solve for L, I have minus 2W from both sides, divide by 2, so I'd have 50 minus W. Okay, and then what's going to happen is I'm able to plug it into my area formula, so I'll highlight this. So I know what L equals. Okay, so I could plug it in for the spot of L. This equals L. Okay, so I'm going to rewrite my area formula. Now it's going to be area equals 50 minus W, okay, times W, which equals 50W minus W squared. Now if you look at this graph of it, for the second step, you're going to be able to see the graph is a parabola that is just facing down, if you think about the graph. Okay, and you might be able to kind of already tell what that's going to equal, but we have area as our y-axis, and then we have x is our width. Okay. And if you look at this tops point, you know that's where your derivative equals 0. So if I find the derivative of my area with respect to w, not time anymore, okay, it's going to be 50 minus 2w. If I set that equal to 0 and solve for w, so minus 50 from both sides, divide by negative 2, w would equal 25, which is not surprising, okay, because what's going to happen is if you plug in w back for what length equals, you're going to see that length also equals 25. And that should make sense, right? A square would give you the largest area. So I'm going to make a concluding statement. I'm going to say area is maximized when length equals width, which equals 25. Okay, and this is a square. All right, second example, number 2. Ask you another situation. In this case, I'm going to say which points on the graph of y equals 4 minus x squared are closest to the point 0, 2. Okay, so what I would probably do again is put down everything that you know, so kind of draw a sketch of it. You know that 4 minus x squared is going to be, let's see, you have vertex at 4, you have a point 3, negative 1, 1, or 1, negative 1, 3, 1, 3, and then it also goes through 2, 0, and negative 2, 0. So here's our graph, and it's closest to the point 0, 2. So I'm going to draw that in a different color. So when you're looking at this, you can kind of see already, you know, you don't know exactly, but it looks like there's probably going to be 2 spots where that happens. Okay, so we have a sketch of it. Kind of thinking about what formula you'd want to use. I don't really know if you remember, but we have the distance formula. Okay, where we say, based on the Pythagorean theorem, basically d squared equals x minus x1 squared plus y minus y1 squared. Okay. And when we look at that, we're going to say, okay, well, how could we kind of get it all in terms of one variable? What do we know what's going on? And it might be easier to rewrite this where we have d by itself, so it equals the square root of x minus x1 squared plus y minus y1 squared. Let's see, from there, I know that x1 is 0, y1 is 2, so I could probably say, okay, well, d equals the square root of x minus 0 squared plus y minus 2 squared. Okay, I still have a couple of variables. We also know what y equals. It's in terms of x up here. So we could plug that in. So y, y was the 4 minus x squared minus 2, all of that squared, with x squared plus, so I'm going to have 2 minus x squared, all of that squared. Okay, so I'm kind of now have an equation that's all in terms of a variable. Note that your distance is going to be the smallest when the expression side of the radical is the smallest. So although we could take the derivative of what we have for this equation right now, really, if we just look at the inside, okay, I'm just going to make a note here. I'm going to say note. Okay, d is the smallest when the expression inside the radical is smallest. Okay. So I'm just going to actually make an equation from the inside of what I have. So I'm going to say f of x equals x squared plus 2 minus x squared, all of that squared, if I find my derivative. And you might want to look at the graph of this. It's kind of interesting because you're going to have a couple points that could be max or min. I have x squared minus, if I FOIL this out, it'd be 4 minus 4x squared plus x to the 4th. And if I rewrite this, it's going to be x to the 4th. Let's see. Oh, excuse me, back here should have been plus. I was looking at my work. X squared minus 4x squared is going to be minus 3x squared plus 4. If I set that equal to, now, I'm sorry, this is not my derivative, this is just my function. I haven't taken my derivative yet. Now if I go ahead and take the derivative, it's 4x cubed minus 6x. If I set that equal to 0, I'm going to factor out a 2x. So I'm left with 2x squared minus 3. So that means it's going to be when x equals 0 and when x equals plus or minus root 3 over 2. Now when you look at x equals 0, that's probably the furthest distance that we would have. It's not going to be closest to, and if you also looked at the original graph of that function, you would see that that is not your relative max. So I'm going to take that out of the possibilities. And that just means the last steps we want to think about my ordered pairs. So if x is root 3 over 2, we need to find y, and then also negative root 3 over 2. Go back to my original equation, y equals 4 minus x squared. So then I get y equals 4 minus 3 over 2, which is just going to be 5 over 2. Do the same for the other one. Now, hopefully you're going to notice that if it's squared, okay, we still end up with the same thing. It's 4 minus 3 over 2, so it'll also be 5 over 2, which should make sense. Okay. Alright, so you have some problems to practice tonight. Let me know if you have any questions.